Today our topic of discussion is transistor biasing. As we know that there are three terminals of a transistor. One is known as emitter terminal, another is known as base terminal, and third one is the collector terminal. We make a ohmic contact in each space of the three parts of the transistor, and from this ohmic contact we take three wires so that we can connect our battery. Let us consider this is our input side and this is our output side, and in the input side we connect a battery in such a way that the input side becomes forward biased and the output side become reverse biased. Now we will see what happens when the input side, that is the junction J1 emitter base junction, becomes forward biased. If the transistor is of NPN type, it means we have to connect a source of voltage or potential like that. The N type semiconductor is connected with the negative terminal of the battery, and the P type of the semiconductor, that is base, is connected with the positive terminal of the battery. Now we will name this voltage source or potential source like VBE. We can mention it like VEB or VBE. It depends from which point the positive potential, positive terminal of the battery is connected. Here the positive terminal of the battery is connected with the base junction, hence the B is taken first, and the negative terminal of the battery is connected with the emitter, then E is taken after B. It means this is the correct notation and this is the incorrect notation in our case. On the second hand side, we have taken the output side, that is collector and base terminal. We are considering these two terminal in the output side and we are going to make it reverse biased. In this case, we know that in reverse biasing, the N type of the battery is connected, N type semiconductor is connected with the positive terminal of the battery, and the P type semiconductor is connected with the N negative terminal of the battery. Now you can easily find out whether we mention this source as VBC or VCB. We clearly see that the positive terminal of the source is connected with collector, hence C is taken first, and the negative terminal is connected with base, B is taken after C. It means this is the right notation. Hence let us consider again in the input side we are taking a key, that is K1, and in the output side again we are taking the key K2, and we will see what happens when K1 and K2 are alternately open and closed. Let us consider the first case when K1 is closed and K2 is open. It means when K2 is open, this loop is not completed, as this side is open, this is not connected. If this side is not, this loop is not closed, it means there is no current in this side. If there is no current in this side, it means the collector current IC in this case is equal to 0. Whereas if K1 is open, it means we are making this connection. This means this loop will work. It means the current from the positive terminal will move towards the negative terminal of the battery. If K1 is open, the whole electrons will move to the base, and these electrons from base move towards the source and they will complete a loop. Hence in this case total emitter current will be equal to total base current, and we will have IC is equal to 0. On the second case, if we consider K1 is open and K2 is closed, what will happen? If we are considering now this is closed, if this is closed, it means the whole loop will work. But we also know that it is reverse biasing. The PN diode, that is base, and the N diode, that is collector, they are in the reverse biasing, and we know that when there is reverse biasing, there will be no current, and if there is a small amount of current, it is due to the breakage of covalent bonds in these two regions, and due to the breakage of covalent bonds, we will get extra electrons and extra holes in this region, and due to the battery, the electrons will move towards this side and the holes will move towards this side. It means we will have a small amount of current, and that is known as leakage current. And in this case, the leakage current is moving through the collector, and hence it is known as ICO. It is represented as ICO, that is the leakage current through the collector when the input side is open, that is emitter base junction is open. It is not have given any type of source, any type of potential. What will happen in the second case when K1 is open and K2 is closed? In this case, when K1 is open, it means this loop is not complete. If this loop is not complete, electrons from the emitter region will not move in the collector region through the base. Only the current is due to the minority charge carriers present in the, that is, base and collector junction. Hence in this case, IE is equal to 0 and IC is approximately equal to 0, or we can also say that IC is equal to the small leakage current due to the minority charge carriers in the base and collector junction. There are 4 types of transistor biasing we can take into consideration. For example, let us assuming which will be the 4 cases. We have 2 junction. First junction is our, that is emitter base junction. Second junction is our collector base junction. What are the possible cases? What are the possible options in these 2 junction or at the 2 junction for where we can apply the biasing? Let us consider the first case. In first case, we are taking emitter base junction in forward biasing and the collector base junction in reverse biasing, and this is known as the transistor is working in active region. We name it, that is transistor is working in active region. In the above diagram, we discussed this same case, and in active region we find out that transistor is working normally, that the operation is normal, in which the input side is not independent of output side. Output is depending upon the input. If the input side is forward biased and the output side is reverse biased. If we consider this case, what we can discuss here. Let us consider we have an NPN type of transistor, and we have 3 ohmic contact in the 3 spaces or 3 regions of our transistor, and this is our emitter, this is our base side, and this is our collector. In this case, where the input side, that is the emitter base junction, is forward biased, we can add a battery in the circuit like that. Emitter is connected with the negative terminal of the battery, as emitter is N type and base is P type. The base is connected with the positive terminal of the battery, and the battery or the source is named as VBE. And on the second terminal, that is the collector base terminal, which we are going to be reverse biased, as the collector is N type, the battery terminal, negative terminal of the battery is connected with the N type semiconductor, that is collector, and the base, which is P type, will be connected with the negative terminal of the battery. This is our positive terminal and this is our negative terminal, and we will call this source as VCB. Now we will discuss about the working of our transistor in this special case, that is the normal case where input side, that is emitter base junction, that is our first junction, is forward biased, and our second junction, that is collector base junction, is a reverse biased. In this case, as this loop, that is this diode, that is the first diode, emitter base diode, is forward biased, it means there is a flow of current, there is a flow of electrons. And in this case, where the collector and base junction is reverse biased, it means there will be no current in this side of base and collector for their self. The collector current totally will depend upon the emitter current. Hence, IC is directly proportional to IE, and we know that IC is always less than IE, because in our previous lecture, that is transistor part 1, we find out that if there are 100 electrons here, 5 electrons will undergo recombination, and the electrons which undergo recombination will be produced by our source, and they will give us our base current, and the remaining electrons will move towards the collector junction and will produce our collector current. And as a whole, the total current, that is IB plus IC, that is collector current and base current, is a combination, give us the total emitter current. And in this case, in this particular type of option or condition, here the output side is totally dependent on the input side, which we require in our amplifiers. Hence, this type of case or biasing is required in the amplification, where we use the transistor as an amplifier. Next, what type and what is the magnitude of these two voltage sources? As I mentioned here, this particular type of potential is giving forward biasing, and we know that in case of silicon, it is the potential barrier is of 0.7 volt, and in case of germanium it is of 0.3 volt. Hence, if our base or the wafer of this particular type of transistor, it is made up of silicon base, then this potential may be of 0.7 volt, and if this wafer or this base or the whole transistor is made up of germanium, then it will be of 0.3 volt. On the other side, we have reverse biasing. In the case of reverse biasing, we know that we have to work the diode in before the breakdown, and before the breakdown, the voltage in the reverse biasing may be like between 3 volt to 20 volt. It means in case of reverse biasing, we have to apply this amount of voltage, this range of voltage, and in case of forward biasing, we have to apply the voltage approximately nearly 0.7 volt in case of silicon and 0.3 volt in case of germanium. Here we find out that the collector current is totally depending upon the emitter current. In second case, let us consider the junction J1 is forward biased and junction J2, that is our collector base junction, is reverse biased. This is the case where we get the let us consider the junction J1 is reverse biased and the junction J2 is also reverse biased. Here we find out that our transistor is working in our cut-off region. Now we will discuss the how the transistor will work in cut-off region. Again, draw a block diagram for NPN transistor and show the three regions and the three terminals of NPN transistor. Let us consider these are the ohmic contacts and we are obtaining the three terminals after the ohmic contact. In our case, we are discussing the reverse biasing in the junction J1 and reverse biasing at the junction J2. Let us consider this is our input side and the input side is reverse biased. If this is reverse biased, how we are going to connect our battery source here? This terminal will be connected with positive terminal of the battery and we will name it like VEB because positive terminal is connected with emitter and the negative terminal is connected with base. On the second side, again the output side, we have to give reverse biasing to our output side and we know that the collector is N-type semiconductor here and we will connect our positive terminal of the battery and the negative terminal of the battery is connected with the base which is P-type semiconductor. Hence we are having reverse biasing on both junctions, that is emitter base junction and the collector base junction. What will happen in this type of biasing? We know that in reverse biasing there is no current on the output side and there is no current into the input side and the transistor is not working. And if IE is equal to 0, IC is equal to 0, it means the transistor is in cut-off mode. Transistor is working in cut-off region. This region is not of any use for transistor working as we are not giving any type of input and we are not having any type of output. It is working like that is the switch is off. It means when both sides are reverse biasing, our transistor will work as an open circuit. It means there will be no current in the input side and the output side. But in reverse biasing, there is no current due to the majority charge carriers, but we know that at room temperature we have some holes in emitter and some holes in collector and some electrons in base, and due to these minority charge carriers and the direction given by the source, voltage source, these minority charge carriers will form a loop and there will be a small current due to minority charge carriers. Small current, and it is due to the flow of minority charge carriers and there is no current due to the majority charge carriers. The third case, which is in this case we will take our J1 junction forward biased and J2 junction also forward biased, and this is the condition where the transistor will work in the saturation region. Now we will discuss what is the saturation region. Let us again consider we have an NPN transistor and we have made three ohmic contacts, one at the emitter side, another at base side, and third one is as collector side. This is our junction J1 and we have to give it forward biasing, and in forward biasing the n-type semiconductor is connected with the negative terminal of the source and the p-type semiconductor is connected